Hello friends, today I will discuss the open circuit test on transformer. This is also called no load test on transformer. First, we consider what is the necessity of this test. The necessity is to get the equivalent circuit of the transformer at no load condition and also to get the core loss of the transformer. And coming to the assumptions in this test, the copper loss is neglected because the no load current is only 3 to 5% of rated current. And next, the rated voltage applied to the primary winding, that is LV winding in this case, is low, and that value is rated voltage. And the wattmeter that we use here is low power factor wattmeter, and the range of power factor that exists normally is 0.1 to 0.35. And when the circuit is observed here for no load test, the secondary winding is open circuited and the primary winding taken here is LV winding. Primary winding means the winding which is connected to the supply is called the primary winding. The winding which is left over or connected to the load is called the secondary winding. In this case, LV winding is connected to the supply via a variac, ammeter and a wattmeter and voltmeter. And here voltmeter is connected directly across the LV winding, and the wattmeter connected here is LPF wattmeter. And if we observe here, this is the current coil of the wattmeter and this is called the potential coil of the transformer. In the potential coil of the wattmeter, the inductance and the resistance of the potential coil is very high, and whereas the resistance of the current coil is very less. So the terminals of the current coil is represented with ML, and whereas the potential coil of the wattmeter is represented with C and V. And this total meter is called the wattmeter, represented by W0. And here this is the variac connected to the single phase AC supply, and this is connected to the ammeter, and this ammeter reads the no load current represented by I0. So the procedure is like this. First, switch on the supply here and vary this variac such that the voltage applied across the primary winding, that is LV winding, is rated value, that is represented by V0 here. Until V0 is obtained, this variac point should be varied. Under that condition, note down the ammeter current, that is called no load current. Similarly, the wattmeter reading should be noted as W0, and this W0 indicates the core loss of the transformer, but we neglect the copper loss of the transformer because the no load current is only less than 5% of the rated current of the transformer, and that low current flowing through the primary winding means automatically the copper loss in that will be neglected. But whereas the applied voltage is rated, so the core loss can be calculated, obtained, and that is measured by the wattmeter. And because the power factor of the no load transformer is very low, that is 0.1 to 0.35, the wattmeter used here is LPF wattmeter. So applied rated voltage is represented as V0, and the no load current shown by the ammeter is I0, and W0 represents the core loss. And as we know, the core loss or real power can be written like this: W0 is equal to V0 I0 cos phi naught. From this, the no load power factor also can be calculated, that is cos phi naught is equal to W0 by V0 I0. And for this we can draw the vector diagram under this no load condition, and this is the applied voltage Vp or V naught, and this is the flux line which lags the V naught by 90 degrees like this, and we say Im is in phase with phi. This is called magnetizing current, and similarly Ic is in phase with the applied voltage V naught, and the resultant of Im and Ic is nothing but I naught. This value is shown in the ammeter. And having known the power factor from this formula, phi naught can be calculated. Once phi naught is calculated, the position of the I naught can be fixed like this. And similarly, primary winding also induces voltage and secondary winding also induces some voltage. And primary induced voltage we represent with EP, and secondary induced voltage we say that is ES. Once we look at the vector diagram here, cos phi naught can be calculated as IC by I naught. This is IC divided by I naught. And from this, the active component or real power component or the core loss component of the no load current can be calculated as IC is equal to I naught cos phi naught. And no load loss or core loss can be written like this: V naught into IC, and this is already known as the wattmeter reading, so we can equate that. So W naught is nothing but equal to V naught IC, and we know IC is nothing but I naught cos phi naught. Substitute this IC value here, then we get W naught is equal to V naught I naught cos phi naught. And from this vector diagram, we can also write what is called the sin phi naught. So from sin phi naught we get Im by I naught like this. From this we can calculate what is Im. Im is nothing but I naught sin phi naught. What is the necessity of calculating this IC and Im? To calculate the no load components of the transformer, we need this. And we know what is I naught. I naught is nothing but vector sum of IC and Im. So we can write I naught is equal to root of Im square plus IC square. And once we draw the equivalent circuit for this condition, we get the equivalent circuit under no load condition for the transformer like this. This is the applied voltage and this is the no load current, and no load current will have the two current components. One is active component, the other is magnetizing component like this, and the active component flows through the no load resistance or not, and whereas Im flows through the X naught value. In the induced voltage in the primary winding we represent as E1. And once we know this, because this is in parallel with V0, so V0 V E1 are one and the same, so we can calculate what is R naught, what is X naught. R naught is nothing but V naught by IC, and similarly X naught is nothing but V naught by Im. So having known this Im value and IC value, we can calculate what is R naught and what is X naught. Once R naught, X naught are known, so we can draw the equivalent circuit corresponding to the no load test on transformer like this. V naught, this is R naught, this is X naught, and the current flowing here is IC, and current flowing here is Im, and here the no load current is I naught, which is represented in the ammeter. Next, short circuit test on transformer. Why should we conduct the short circuit test on the transformer? There is a reason for this. The assumption is here that we apply the rated current to the primary, and here we choose HV as the primary winding and LV winding is short circuited. The reason for making HV winding as primary is that so to pass the rated short circuit current or rated current through the transformer, the voltage to be applied is only 5 to 10% of the rated voltage of HV winding. So that is the reason the primary is always HV winding for SC test. And then, and power factor in this test is normally unity, and because the power factor is unity, so the wattmeter to be connected in the circuit should be UPF wattmeter, like this. And this UPF wattmeter is represented with the WSC, and the short circuit current is nothing but the rated current that flows in the primary winding, and corresponding voltage is nothing but applied voltage is nothing but VSC. The procedure is like this. So connect the variac like this to the supply, single phase supply, and this variac point should be connected to the ammeter like this, and the ammeter other terminal should be connected to the wattmeter current coil like this, and the current coil should be connected to the primary winding, and here the potential coil of the wattmeter should be connected across the supply like this, and here the wattmeter also connected across the supply, that is variac, that is VSC, and here first the variac should be kept at the minimum position, then varied slowly so that the ammeter current is shows the rated current of the HV winding. Once the ammeter reaches the rated current of HV winding, then the movement of the variac should be stopped. Under this condition, note down the wattmeter reading WSC and also voltmeter reading, that is VSC. Once these values are noted, then we can say this WSC is nothing but a copper loss. And this WSC also can be written as ISC square into RSC. ISC square means rated current in the primary winding whole square into RSC, means this is nothing but the equivalent resistance of the transformer under short circuit conditions referred to the HV winding. This RSC can also be written as RHVT, means the equivalent resistance of the transformer referred to the HV side. And once this is known, we can also calculate what is RSC value. RSC is nothing but WSC divided by ISC square. And we also can calculate ZSC under this condition, that is ZSC is equal to VSC by ISC. And this ZSC is nothing but the equivalent impedance of the transformer referred to the HV side. And similarly, XSC is nothing but the inductive reactance referred to the HV side, that is represented by HVT. And this XSC can be calculated using ZSC and RSC, that is root of ZSC square minus RSC square. So once this HSC, XSC and RSC are known, then the equivalent circuit can be drawn like this. Look at this. So whatever values are calculated there, RSC and XSC, can be shown in the circuit for the HV side. And this is E2, and this is the load, and load terminal voltage is V2. So under short circuit test condition, this is the equivalent circuit we get, and whereas under open circuit condition, this is the equivalent circuit of the transformer, that is applied voltage is rated voltage to the primary winding, and then the current that it flows here is IW, IM, and the values are I or not X naught. And whereas for short circuit test, the equivalent circuit is this. And if you observe here, the number of turns on primary or N1 means less number of turns, whereas the secondary side voltage winding is HV winding and the number of turns are more. So the number of turns we say as N2, and the current that flows here we say I2 or ISC. So the whole purpose of conducting the open circuit test and short circuit test on transformer is just to know the equivalent circuit of the transformer